Bingo, 1 o'clock rock. I'm so happy to be here with Henrietta Dulai. Welcome to the show, Henrietta.
Thank you. Glad to be here.
Dr. Henrietta.
Oh, Henrietta is fine.
So Henrietta is a very special person. First, because she has the same first name that my grandmother had. That makes her special, ab initio. That's important. But the other is that she's an associate professor at the Department of Geology and Geophysics at SOWEST, the School of Ocean and Earth Science at UH Manoa. And she's studying and working in radioisotopes in coastal hydrology. That's why we're calling this show Fukushima Fingerprints Coming to Hawaii. You'll see what I mean in a minute. So tell us what you do, Henrietta.
So because of my education, I learned to use radioactive elements to study Earth processes. Specifically, I focus about water, the water cycle, how it flows from the land to the ocean, what happens to different chemicals then within the ocean, what can we learn about ocean currents, and how the chemicals coming from the land to the ocean by water flow support biology and other processes in the ocean.
That's it?
In a nutshell. But
Let me
then it goes too much wider. Yes.
Henrietta Dulai is a geochemist who uses chemical tracers, that's always exciting, to study coastal hydrology and biogeochemistry. I never heard that one before. In this episode, we hear about her use of radiochemistry, I never heard that one either, to investigate the dispersion of Fukushima-derived radioisotopes in the Pacific. That's really exciting. You're in the top 1% of exciting scientists. Wow, exciting. So what is with all of these radio things and radioactive, I guess that means? What are you working on in terms of Fukushima?
Right, so I alluded to the hydrology part, and as you just said, that's my everyday, what keeps me busy and is fun, that I use natural radioactivity to learn about processes. But then when Fukushima happened, I thought, okay, this is something we have to follow up on, and how can we use all the radionuclides, not just to learn how bad or what are the levels of radioactivity from Fukushima that came to us, but also to learn about ocean currents or precipitation patterns and other information that these radionuclides help us learn about.
So you're learning about the processes by which these radioactive elements are carried around the Pacific.
Correct.
Before the show, I was telling you, I'm so impressed with SOWEST and UH Manoa. We know so much about the Pacific. We know everything there is to know about the Pacific. And you're just one of the parts of that at SOWEST. We know the weather, we know the water, we know the air, we know the biochemistry of the ocean, we know the bottom of the ocean, the top of the ocean. I mean, you could, even on this show, sitting in that chair, we have learned so much about what goes on in the Pacific Ocean. There's a lot to learn, but UH Manoa is really on top of it. I'm so impressed with that. You ought to know this. You ought to know. You ought to be, you ought to admire Henrietta and all her colleagues that study the Pacific Ocean know so much about it. So, okay, so we're going to find out what happened to all that radioactive debris that was drifting off Fukushima. What's the path it takes?
So let me stop right there to tease that question apart. Yes, there was a tsunami that released the debris, and that debris started moving offshore with the currents taking them and diluting the patch. But it traveled along...
The garbage patch, referred to affectionately by the scientific community as the garbage patch. Yes.
And the Fukushima power plant disaster happened a few days after the tsunami. So the leakage of the radionuclides started on the 12th, 13th, and 14th of March. So the patch or the plume moved a little bit offshore already when most of the deposition happened. So the debris itself did not carry much radioactivity on it, only what fell on it. So it wasn't soaking in the discharged waters much.
Okay.
So we have tested different items that were caught that were shown to originate from Japan. Never found any significant levels of Fukushima-derived radioactivity on them. So the plume itself, the debris, was not...
What is a plume?
I define the plume as a consolidated or organized patch that travels with the current.
Okay. And before we get too much further off that, why does the plume stay together? What are the physical processes that keep it together in a plume?
So processes in the ocean that are not just major big currents that move the plume, but then smaller eddies that cause smaller scale mixing would disperse the debris. So that would make it dissipate, eventually mix.
Eventually it will be dissipated. It's not going to stay together forever.
Well, eventually it will reach the North Pacific garbage patch.
Which is the biggest.
Which is within the gyre.
The gyre. That's
Yes.
the gyre, and that's located northeast of Hawaii and in the lee of Alaska there and the Pacific Northwest, right?
Yes.
Somewhere in there.
Correct, yes.
They probably don't like having it around.
No one does like to
one
have
does. No one
garbage
does.
in their backyard.
Yeah,
Correct.
yeah. How far offshore is it, say from Alaska or the Pacific Northwest?
So we are talking about thousands of miles, but it shifts. And so all the debris that our north shore of the islands get some of it is coming from that.
And
Direction,
the
yeah.
gyre, it implies that it's moving in some kind of circle, some kind of
Yes.
whirlpool effect.
Yes, that is.
That's the way the Pacific works in that area.
Yes.
And it gathers the patch.
Yes. And so these currents, the same currents, were the ones that carried the Fukushima-derived radionuclides, all the ones that get released from the power plants and deposited from the atmosphere. So these currents would then carry the radionuclides that were dissolved, so not as particles or something hard to
But in the
touch,
water.
it's dissolved. So the currents would carry these radionuclides across the Pacific.
So they're just in the water, dissolved
Dissolved
in the
like
water.
a salt. When you
Like
put
salt.
salt in the water, the potassium, the sodium, they all dissolve and that flow with the currents.
But you can sponsor them. I mean, you can see them. You can spot them with instruments. You can spot them with radioactive sensitive radio sensors or something, right?
That's not the choice that scientists use. So physical oceanographers, for example, try to understand the currents based on their temperature and salinity. What we did is there is no sensor that could look down the Earth and say where it's more radioactive than other places. Not even an airplane that could fly would be able to detect such low concentrations as we are talking about.
Low concentration.
So we had to actually collect thousands and thousands of liters, or gallons if you prefer, of water and individually analyze samples, concentrating all that radioactivity into a tiny volume, which then was measured with the
How do you
instruments.
do that? So you take a bottle and you scoop up the water, and now you have thousands of bottles of water in a given place.
Yes.
How do you concentrate it?
So we specifically we focused on cesium isotopes. Those were released from Fukushima in the largest quantities that would directly affect the environment. And so it's also easier to measure and behaves differently than iodine, which was also released. So cesium would deposit with wet deposition from the atmosphere and also was released by water masses. And so we would go to places where we wanted to see whether that cesium plume is there or not. We would take a 100-liter sample. 100 liters, filter it through this tiny column of little beads, organic beads, so organic material that can preferentially capture cesium out of the water. So as the water flows through these beads, the beads collect the cesium, the rest of the water and other ions simply pass through. And then we have the beads that are concentrated, that concentrated out all the cesium from the water.
That's radioactive.
And so cesium, there were 2 cesium isotopes released from Fukushima. One has a 30-year half-life, so will be around with us for another 100 years or so. And the other has a 2-year half-life, cesium-134, which decays. So within 5 half-lives.
Yeah, so
it will
we're
decay.
done 5 years
Not
ago,
yet,
wasn't it? Yeah.
not yet. So it's been only 2.5 half-lives. So
Yeah.
it takes about 5 half-lives, so
Oh, I see.
10 years
To really go.
for it to go.
So, but, and if you went, say, to the Atlantic Ocean, but they didn't have Fukushima, and you started making the same collection, you'd probably be able to find some cesium there too.
Oh, definitely.
Yeah.
So the cesium story in the ocean started in the 50s when we were testing nuclear weapons above ground, blowing up atolls and so
like
forth.
Bikini Island. Ooh.
Exactly. So there is, yes, a big environmental problem
Yes.
that was not planned.
There's a book by Simon Winchester from the East-West Center called Pacific, just the word Pacific. And the first chapter in this book is the detailed discussion of what happened at Bikini. It will make you sick to read this, make anybody sick.
Right.
Pacific by Simon Winchester, it's worth getting it. Amazon, yeah. Sorry.
Right, so a lot of cesium was released already in the late 50s and early 60s, and that cesium is still around with us. And so back then, huge amounts of cesium were dispersed. The same kind that was released from Fukushima, but because of the differences in half-life, the short one has been gone, right? So within 10 years or so. The other one is still around, and we can detect it all around the world, not just in the ocean, but on land also.
And all this from the cesium at Fukushima.
No, I'm talking about the nuclear weapons.
Oh, it's talking about Bikini. So it dispersed
the nuclear
from
weapons.
there. And that's what, how many years ago? It's 60, 70,
Yes.
60 years ago.
Yes, and then Chernobyl added a little bit to that, but other sources also, man-made sources, reprocessing plants release some of the cesium into, like Sellafield, into the Irish Sea.
Do I care? Do I care about cesium? For example, if the waiter comes and he says, "How would you like your martini?" and I would say,
With
put a little
cesium?
cesium in there. Would I want cesium in my martini?
Probably there is some already in there.
Oh, no, don't say that.
but that's the point here, that the message I would like to get across, that yes, we are aware that radioactivity is harmful, yet we have been living with it all around us forever, because there are these natural radionuclides that probably have higher levels of radioactivity than the cesium. And I don't mean to say that it's okay to have cesium in the environment. I'm just saying that we have been living with radioactivity all along. Our bodies, for example, have, let's say, use an example of potassium, natural potassium, about 140 grams or so. And I looked this up. I have not measured that, but this is an accepted literature value. Our body has about 140 grams of potassium, out of which some of it is radioactive, and it's natural. And that radioactive part gives us an inventory of 5,000 becquerels of potassium-40.
Potassium-40 is radioactive.
Yes. So becquerels are the unit that we use for radioactivity. That means how many decays we see per second from a certain amount. So our body has this natural radioactivity. So if you add a few atoms of cesium to it, I'm not saying it doesn't do an added effect, but
it doesn't
you
help.
see my point. It doesn't help. It doesn't help.
Yeah.
But if you add 1 or 2 to the 5,000, it's
You don't know what the
it's not
combination of the cocktail effect, yeah? Yeah. That's why I was talking about martinis. We're going to have one now. It'll be very quick. It'll be a 1 minute martini break. We'll be right back. You'll see. Henrietta Dulai. We'll be right back.
Hi, I'm Ethan Allen, host of Likeable Science on Think Tech Hawaii. I hope you'll join me each Friday afternoon as we explore the amazing world of science. We bring on interesting guests, scientists from all walks of life, from all walks of science, to talk about the work they do, why they do it, and moreover, why it's interesting to you. What the science really means to your life, its impacts on you, how it's shaping the world around you, and why you should care about it. I do hope you'll join me every Friday at 2 p.m. for Likeable Science.
Aloha, I'm Kaui Lucas, host of Hawaii is My Mainland, here on Think Tech Hawaii every Friday afternoon at 3 p.m. Start your Pauhana weekend off with the show where I talk to people about issues